All right, start with the warm-up here. So the idea is we're going to do a little bit of linear algebra review because it's going to be an important part of this chapter. So we'll start off with some basics here. I got a matrix, I got a vector, matrix vector multiplication. So here I am just writing my matrix, writing my vector, doing the product as the dot product of the row and the column. So that means my first component would be 3 plus 8. All right, then I look at the second component of the vector result here as the dot product of the second row and the column. I get 9 plus 16. So the resulting vector is 11 and 25. Okay. Lots of ways you can mentally do that. If you have my linear algebra class, I probably grabbed the vector and moved it and put it on top of the matrix or something weird, right? The important thing is you need to be able to do that matrix vector multiplication. Any questions so far? All right, the next piece is going from a system of equations to a matrix equation. That's something else you did in linear algebra probably over and over again. Okay? So the idea is we're trying to make a matrix equation, looks like AX equals B, something of that form. And the idea is I can grab the coefficients of that U1 and U2 piece. So I got 3, 2, 6, and negative 5 times the vector U1, U2. That's equal to the vector 4, 3. Okay, so you should be able to go quickly from that system of equations to that matrix equation. And if you've done that once again, linear algebra over and over again, it's just like generating that auxiliary equation for high order. It's a process, you just write down the auxiliary equation. What I'm doing is grab this and I'll write down the matrix equation. But it's really important to understand, where it's coming from and the operations that get you there. So just to model that real quickly, I'm just going to multiply that side out. If I do that matrix multiplication just like we did, I would get that row dot product with that column. I get 3u1 plus 2u2. I can see that's the left-hand side of that first equation. Right? The first component of that product. Then the second component would be the dot product of that row in the column. I get 6u1 minus 5u2 equal to this other vector. And the idea is that two vectors here are equal if and only if their components are equal. So the first components have to equal each other. 3u1 plus 2u2 must equal 4. That's that first equation. And the second components have to equal each other. That's the second equation. So just that connection between the systems and the matrix equation. Okay, any questions there? I know linear algebra, previous semester probably rusty, but these are going to be important pieces. Any questions? All right. All right, the plan for today. A couple of administrative notes here. Exams will be returned on Thursday. Yes, that is a fingers crossed emoji, right? Maybe I'm trying. A couple stacks to go through still, so that's certainly my goal. So I'll try to get them done by then. We'll see how it goes. There was a little sub note here that I had about homework assignments. So the idea is this. We're doing a new Canvas website integration thing. It's kind of in beta, I found out this semester. So there are some glitches. One of the problems is that it takes those website assignments and brings them to Canvas. It does not equally weight them. And so more points are more points. I don't like that. I don't always have to be equally weighted. So this is how I'm going to change that. I'm going to change all of your point scores on your homework to be 100. Okay? And when I first do that, don't freak out, right? Because your 8 points will be a much smaller percentage out of 100, right? It will look like that first. But then I go into WebAssign and I run a rescore on all the assignments because when you do a WebAssign, it sends a percentage of your score over Canvas, and Canvas takes that percentage and calculates the points. So when I restore WebAssign, it will assign you a new point value, and when it's over 100, what we get percent. Okay? There's a fill path, there's this transition for a day where your homework score goes like this. Right? We'll revert back to normal in a little bit. Okay? Any questions there? All right. I did that to section 1 yesterday. I forgot to tell them, so they were scared for a little bit there. All right, today's topic is chapter 3. We're going to start on chapter 3, systems of differential equations. here's our roadmap for this chapter. We're going to start by talking about what are systems. We real briefly introduced them in the very first part of the course, but just to show what they are. So now we're going to go a little more detail. What are systems? Why do we care about them? Where are we going to see them in application or in some mathematical process? Then we'll talk about existence and uniqueness, everyone's favorite. Then we'll go through solving the linear homogeneous systems. And the theme for this chapter is going to be it's the same thing that we've already done, just applied to systems. So a lot of the vocabulary is going to be the same. A lot of the theory is going to be the same, just using different notation. Okay? Any questions there? All right. As a reminder, can you please put your phones away off of the desk so that they're not a distraction. Pockets. Thank you. All right. What are systems of differential equations? Here is an example of a system. System is just a set of n differential equations with n unknown functions. So here I have a system. There are n equations, and there are n unknown functions, u1, u2, n. Those are all functions of t. Those are the things we're trying to find. Let's give you maybe a more specific case here. What about d u1 dt? The derivative of u1 is equal to 2tu1 plus t squared u2 plus t cubed. And then du2, the derivative of that guy, is equal to the sine of t times u1 plus 3u2 plus t minus 1. This is a system. I have two equations. I got two unknown functions, the u1 and the u2. Okay. And because I have two equations now and two unknown functions, I will call this guy a 2x2 system. So this is a 2x2 system of first order differential equations. If you can imagine it's a 2x2, if this was an n by n, where n was big, you know, a 10 by 10, 100 by 100, 1,000 by 1,000, possibly, right? I wouldn't want to write that all out, right? My wrist would get tired. We want to clean up the notation a little bit. So we're going to use linear algebra notation to represent this system. Okay? What does that mean? That means if I let u be a vector valued function of t, that means I plug in a value of t and I get this vector of functions that will look like all of my unknown functions, u1, u2, in general down to un. Then maybe in my specific case, just u1 and u2. That's what u is. And I'm also going to say, well, if that's u, what is u prime? What is the derivative of a vector valued function? How do I calculate that guy? And the guess is, yep, absolutely. So I got u1 prime and u2 prime. Whatever those functions are, this would be the derivative of those functions. Okay, kind of setting up some notation here. Now I'm looking at my system. I'm basically doing just what I did before with my regular system of equations. Over here, I'm going to call this a vector, u1 prime and u2 prime. Over here, I'm going to grab the coefficients. I'm really going to think about this as two vectors, that vector and this vector. That's one vector with all the u1 and u2s, and like one vector of all the stuff that doesn't have u1s and u2s. And this one I can represent as matrix vector multiplication, where I grab the coefficients of those u pieces, and I multiply that by u1 and u2. And then I have this extra little vector at the end. Okay. And now the idea is when I've defined this vector function u and calculate u prime, I can now take this matrix vector equation and rewrite it as u prime is equal to some matrix A whose components could be functions of t times my vector function u plus some other vector function, which I'll call f. Now I'm going to use specific notation for my vector functions. I'm going to put those little arrows on top of them. Right, the book just leaves them and defines them as vector functions, and you're supposed to determine them from context. That last notation that's all I got to write. That could apply to this 2x2 system. It could apply to a 1000 by 1000 system. It's still just this guy. The only thing that would change are the dimensions of U, A, and F. Okay? So any questions there? Representing this system using this matrix vector notation. All right. Okay, so now we know how to represent this kind of using the clean notation, but where in the world do these guys show up? Why do we even get this system of equations? There's really two ways we're going to talk about. One is through application. So here's an example from a population model. We've looked at a bunch of populations modeled, right? With exponential growth, the logarithmic model. We looked at another one with harvesting, like an immigration kind of factor. There were different equations that modeled different populations, to account for some of the complexities in those populations. Remember, we looked at the population of the US, that fit that nice exponential growth model. We looked at Japan, that matched that logarithmic model. What about other factors? Here I have a population, let R of t be the population of rabbits, like on some island or something, right? And let W of t be the population of wolves. Dun, dun, dun. No foreshadowing there. How is the population of rabbits changing? Well, we can look at dr dt. And you might guess then that, well, maybe it grows exponentially. We'll just assume it grows exponentially. In which case, the population of rabbits should look like, I don't know, some number times r, right? But then we can also see that, the population of wolves is probably going to affect the population of rabbits. More wolves probably means less rabbits. So we might have this other factor for the rate of change of rabbits, subtract off maybe like 1/2 times W. But what about W? Like, that's not some fixed value. That is also changing. So I might also want to model how the population of wolves is changing. Once again, if I'm assuming some sort of exponential growth just by itself, maybe that would be a good model for the growth of the wolves. But once again, that population is going to be dependent on the number of rabbits, right? More rabbits probably means more wolves, right? Better food supply. So I can imagine there's some other factor here that's affecting the population of wolves. So we can see here we've generated this system of equations. Go ahead and take this system of equations and let U equal rabbits and wolves, and write that out in that matrix vector. All right. We write this guy as U equals A, U prime equals A times U. And really the only question is, what is A? What is the matrix A? 2, negative 1/2, 1/2, 2. That's really the only question. Any questions there? Okay. Now, your book will talk about this model. It actually doesn't write it like this. It says, really, you got your population of rabbits here. but this other factor is actually more closely related to the product of the population of wolves and rabbits. And over here, this is really better represented as the product as well. And so why did I start without that? Well, can we take this new system and represent it in that matrix form? I can't. I can't write this in this linear algebra form. This is a system of differential equation. However, it's a nonlinear system. Right? So we have linear, we have nonlinear systems. It's the linear ones that we're going to be able to write in that matrix form. And just like for higher order differential equations, we had nonlinear higher order differential equations. Did we solve any of them? No, they were hard. Same thing with systems, right? Nonlinear systems are out there, but they're very challenging. So we're primarily going to focus on linear systems. Okay. All right. Where else can we possibly run into these systems? Well, it turns out we can take a higher order differential equation and convert it to a system of first order differential equations. And so you can imagine if we had a big, like a much higher order, a 20th order or 200th order differential equation, I might not want to work on that 20th degree polynomial, right, to find the roots to do my auxiliary equation thing. It might be better if I transform it into a system of differential equation. You need some linear algebra systems to find the solution. Okay? So how do I convert this higher order differential equation to a system? I make some substitutions. Here I have one unknown, x1. I'm going to use two unknowns. I'm going to let u1 equal x. I'm going to let u2 equal x prime. Okay. Now, if I do that, I calculate u1 prime, what does that equal to? Sort of. I'm going to stick with x prime. Okay, but x prime is equal to u2. If I calculate u2 prime, that should be equal to x double prime. Okay. Now I'm going to take my differential equation and I'm going to write it like this. And now I'm just going to plug in my u1s and u2s. X double prime is really u2 prime. And apparently that's equal to negative t times x prime, which is u2, minus x, which is u1. I have one equation for my system. The other equation is going to need to look like this. u1 prime is equal to x prime, which is equal to u2. So this would be my system of differential equations. And the solution to this system should match up with my solution to the higher differential equation. When I solve this, I'll figure out what u1 is, and that should be equal to x. All right. So, if you took that solution and wanted to write it in matrix form, shoot. All right. So if you took that system and you wrote it in a matrix form, right, in that process you have to get the right A. Which one of these is the right A, or is it E, none of the above? And the nice thing is, when you're done, you can just do the multiplication if you want, right? If you write matrix A, then write the vector U next to it, do the multiplication, you should get back to that right-hand side. See what we got so far. C looks pretty strong. That's correct. All right, the idea is that we're kind of want our U2 pieces separately. So this is really the same thing as 0 U1 plus 1 U2 minus U1 minus T U2. And now you grab those coefficients to make C. Wonderful. All right, any questions so far? Okay. All right, so now we have kind of the form. We can write it in our nice clean form. We know we might run into these guys in real life here in some applications. Now the question is, how do we solve them? So the next step is going to be laying the foundation of the theory so that we can eventually solve these linear systems. And there's going to be a big theme again. Once again, systems simply extend the concepts we've already discussed. And so what I'm going to do is I'm going to scroll through this, and it's going to be a bunch of, here's what we did for first order differential equations. Look how it compares to systems. Here's what we did for higher order differential equations. Here's what we did with systems. Okay, so all right, so the first thing we'll talk about is the form of the differential equation. So first order differential equations, in general, we could have them look like this, right? Dx dt equals, in general, some function of t and x. And the same is really true for our systems. We could have a system of our functions here, like that, dot, 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 dot. These are all be primes. And in general, those could be equal to some nonlinear, giant, ugly function of all these variables and their derivatives and a bunch of stuff. Okay? Like we already said, those are hard. Even in first order, we would get lucky sometimes and find out that was separable, or maybe it happened to be exact. But there were certainly cases that we would not be able to solve even in that first order case. So instead we looked at a subclass. It was linear. Same thing here with systems. We'll look at a subclass of linear differential equations, and they will look like this. And you can see the similarity right away in the notation. Okay. In the first order case, we would solve that first order differential equation, and we'd find a family of solutions. And that family of solutions would have some constant in there. Now, to find the value of that constant to satisfy a specific system, to find a specific solution, we need some initial condition. X of t sub naught equals x sub 0, right? Maybe more so specifically, we need x of 0 equals 2. Right, we plug that in to find our constant. Same thing with systems. We can find a general solution of that, but there'll be some constants in there. Okay. To find our constants, we need an initial condition. Our initial conditions will look like this. U of t sub naught will equal some u sub naught vector of value, some specific values. Now I know that's just notation, probably doesn't mean anything yet. In a specific case, we would get u of time equals 0 maybe, and it would equal some initial value like, I don't know, 1, 2. Right, some initial set of values for those functions. Right, this u sub 0, you can really think of as those individual functions evaluated at that initial time. But they end up to be some numbers that we're going to use to plug in there and solve for C. Okay? So once again, focus on the similarity between first order and systems. The next thing we did in first order is we classified them by order, linearity, homogeneity. Okay? For the first time, we looked at the orders of first order differential equations. That's how we kind of labeled them. For systems, we're doing a similar thing, but now we're looking at the number of equations unknowns. We have a 2 by 2 system, 3 by 3, and n by n in general. So that's analogous to the order kind of, right? And we have linearity. And the idea is if we can write it in this linear algebra form, then that is a linear system. What about homogeneity? Well, look at that first order differential equation. Look at the other lines here. Look at this guy. When we look at that, how can we tell whether it's going to be homogeneous or inhomogeneous? What piece are we going to be looking at? F of t, right? The idea is that if that f of t is 0, if it's not there, if there are no extra t stuffs hanging out, then it'd be homogeneous. If there is some non-zero f of t value, it'd be inhomogeneous. Here's an example. dx dt equals 2x plus t. Homogeneous or inhomogeneous? Is that homogeneous or inhomogeneous? All right, that is going to be inhomogeneous, right? We have this extra t piece. Okay. It's going to be the same thing for our systems. It's this guy. If that is a vector of all zeros, in other words, if it's basically not there, now we have a homogeneous system. There's some non-zero vector f of t, and we have a inhomogeneous system. Another way you can tell with the first order one is if x equals 0 was a solution. If you could plug that in to get a true statement, that's another way you could tell whether it was homogeneous or not. It's homogeneous if the trivial solution is a solution. Over here, it's the same thing. If you look at u equals the 0 vector, right? If you plug that in to get a true statement, if that's a solution, you can also be sure that it's homogeneous. All right, so we did our classification. The next thing we did was existence and uniqueness. All right, everyone's favorite. We have this rule for first order differential equations. There's our standard form with our a of t and f of t. We had some theorems, but the net result of all those theorems was there did exist a unique solution pretty much everywhere where a of t and f of t were continuous. That was the net result. And basically the same thing is true for systems. So section 3.2 of the text is pretty long. It's a little bit wordy, definitely technical, right? It's good to go through the details. But the net result is that there exists a unique solution everywhere the a of t and f of t are continuous. That's really what we're looking at. Okay? So you can imagine over here if I had dx dt is equal to 1 over tx plus 3, we'd say there exists a unique solution in the interval from, well, negative infinity to 0 and from 0 to infinity. We said basically for all t such that t is not equal to 0 is another way to write that. And it's going to be the same thing over here. You're looking for bad t values, right? Questions? All right, consider the system. Here is the system. Question 1. Linear, nonlinear. Not 100% sure, about 70-30 here. Well, let's see. I can write this as u prime is equal to 2 negative 1 over t minus 1 t squared negative 4 times my vector u plus 0 negative 1. I've written into that form. So it is linear. Even though there's t squared and 1 over t minus 1, that's still okay. It's linear in the dependent variables. I can't have u1 squared, the cosine of u2. I can't have u1 times u2, right? And that's the case we had up in the population model. So this is linear. Okay? Homogeneous or inhomogeneous? Inhomogeneous, absolutely. Doesn't matter, there's no actual t's over here, it's extra stuff, right? Nothing needs to be all zeros for this to be homogeneous. If I plugged in u equals 0, the derivative would be 0 on the left. That matrix multiplication would end up in a vector of zeros, but I'd have an extra 1 hanging out. So this is homogeneous. All right. Next. There exists a unique solution for all t such that t is not equal to 0, 1, 2, none of these, NA, because there exists a unique solution for all t. And let's stop that guy, start it again. There exists a unique solution for all t in R such that t is not equal to what? Is it 0, 1, 2, some other value that's not listed? Or does it not apply because there exists a solution for all values of t? And we have b equals 1. Perfect. Masters of existence and uniqueness. That's really all there is to it, right? We're looking for problem t's. Any questions? All right. Solutions. Moving on with this trend, the similarity between first order and systems. A solution is a function that satisfies the differential equation. So the idea is that we had solutions. Here's an example. I'm saying this could be a solution. X equals some constant e to the negative 3t. Is it a solution to this differential equation? How would we show that? What do we have to do? Take the derivatives and plug it in, right? That's that big theme, right? You make some guess at a solution for them, take the derivatives, plug it in. And so that's exactly what we do. We would take x prime, take x double prime, we plug it in, see if we get 0 equals 0, right? Or some identical statement. It's going to be the exact same thing for systems. In a system, you might have some solution that looks like this. How about some constant times e to the negative 2t and then 3e to the negative 2t. All right? And that's the solution to some system like that. Or we would know A. Well, how do we check? Same thing. You take the derivative and plug it in. You calculate u prime to be some constant, negative 2e to the negative 2t, negative 6e to the negative 2t. Right? You plug that in for u prime. You plug in u for u, multiply a times u, and you see if you get a true statement. So the process is exactly the same, just different. Right? All right, solution or not a solution? All right, pretty mixed here. Let's check it. All right, so I got to plug it in and see if the left side equals the right side. That's the big idea. So let's look at the left-hand side. calculate the derivative. All right, so this is my u. U prime is just going to be constant, stays there. Derivative of each piece, I have negative 5 e to the negative 5t, negative 10 e to the negative 5t. Then I got to calculate the right-hand side. Right-hand side is basically this matrix times u. So it should be this thing times u, c e to the negative 5t, 2e to the negative 5t. Now I just got to do that multiplication. Now I'm going to clean some things up first. You know, I have e to the negative 5t, but for any value of t, that's just some number. Right? And so basically I can factor that out of my vector. I can certainly rewrite this then as c times e to the negative 5t, 3, negative 4, 4, negative 7, times the vector 1, 2. Okay? I can do that just using matrix vector properties here. Right? When I take a vector and I multiply it by 2, what am I doing? I'm multiplying each of the components by 2. Well, one vector is just multiplying each of the components by e to the negative 5t. So the same thing as taking a vector 1, 2 times e to the negative 5t. Fold out, the scalars, move to the front of the equations, rewrite like this. Now this makes my matrix vector multiplication a little bit easier. Okay? So you don't have to do that. It's just a simplification. So now I'll just do that matrix vector multiplication. And that stuff times this stuff, I get 3 minus 8. And then that times that, I get 4 minus 14. Looks like I get c e to the negative 5t, negative 5, negative 10. Okay? And so I can see that the right-hand side is the same as the left-hand side. So it is a solution. Any questions there? All right. Okay, so far we've been doing a lot of comparing it to first-order differential equations. First-order systems look a lot like first-order differential equations, but they act a lot like higher-order differential equations. A lot of our fundamental theory ideas are going to be really closely related to the higher-order systems. Okay. So now we're going to do the same kind of comparison walkthrough, but now with higher-order differential equations. Okay. All right, so one of the first things we talked about, one of the most important things we talked about with respect to higher order differential equations was that the solutions to an nth order homogeneous linear differential equation form an n-dimensional vector space. That was really the core of a lot of our ideas. The solution space was a vector space. That allowed us to apply all the things we already learned from linear algebra right to our solutions. And the idea is the same for systems. For systems, the solution to a n by n homogeneous linear system of differential equations form an n-dimensional vector space. Once again, it's the same, right? It's pretty much the same. Now, why did we care that it formed a vector space? Well, one reason is because it let us know information about our solutions. When we talk about higher order differential equations, it's great. It's a vector space. That means if I have one vector, one solution x1, and another vector, another solution x2, any linear combination of these two guys is also a solution space. So we knew how to generate infinitely many solutions. Okay. Now the reason for that is because a vector space is closed under vector addition and scalar multiplication. Okay. Engineers, however, didn't realize that we already knew this stuff. We already gave it a name. So They decided to call it superposition principle. You might hear it in the course of refer to that. Same idea. Just different language. Same thing is true with systems now. Exactly the same thing. I have a solution, u1, right? Which is some vector of functions, u1 of t, u2 of t, dot, 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 right? I have some other vector of solutions, okay? Like that. If those are both solutions to the system, then some constant times u1 plus some constant times u2 is also a solution. This is a new property of systems, but it's the same thing we did already, right? Same idea. Okay. Now that statement was actually just a precursor to the bigger statement, the more important statement, because the thing we wanted to do was find the general solution to a differential equation. And so for higher order, we said the general solution can be written like this. C1x1 plus C2x2 plus dot, dot, dot plus, how high did I have to go up? N. Cnxn. For an nth order differential equation, I can represent my general solution as the linear combination of n solutions, but not just n solutions, n linearly independent solutions, right? I needed n linearly independent solutions to form that general solution. Why? Because that was forming a basis for the vector space. Okay? And the whole idea of linear algebra is that I don't care what my vector space is, whether it's functions here, whether it's vector functions over here. The properties are all the same. So I can still form a basis of n vectors. So once again, over here in systems now, my general solution is just going to be some constant, u1, some constant, u2, dot, 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 dot. I'm going to need n of them. And that will be the general solution for my system of differential equations for an n by n system. It's like you're learning a bunch of new stuff without having to learn a bunch of new stuff, right? That's good. Questions so far? Okay, so I want to find the solution of my system. So far I know that all I need is n linearly independent solutions. Okay, linearly independent. That was that piece. All right. Are those guys linearly independent? How do you check to see if they're linearly independent? What was that? Wronskian, absolutely. Right, to check to see if they're linearly independent, I form my Wronskian, which in this case was like x1 and then the derivative of x1. I needed that derivative to get that second row of this Wronskian guy, right? Over here I had t, the derivative gives me 1. I do the calculation, e to the 2t minus 2e to the 2t to the 2t, right? Which is not identically equal to 0. So yes, linearly independent. Now over here I have u1, which is equal to 1, 1, e to the negative 2t. I have u2, which is equal to 1, negative 1, e to the negative 6t. Are those two vector functions linearly independent? What crazy new method must I use to determine whether they're linearly independent? Right? Nothing. I just do the Wronskian. But now the Wronskian is actually kind of easier because I don't have to calculate the derivatives because they already have enough values to get me my square matrix. So now I calculate the Wronskian like this. The first column is just this guy. It's e to the negative 2t and e to the negative 2t. Right? My first thing in my Wronskian is just u1. The second column is going to be second one, e to the negative 6t negative e to the negative 6t. That's it. Product here is negative e to the negative 8t minus e to the negative 8t. So I have negative 2e to the negative 8t, which is not identically equal to 0. So yes, those two are linearly independent. Questions so far? Okay. So for higher order linear differential equations, we knew that if we found two, we could then show they're linearly independent and form our general solution. Did we do that a whole bunch of times? Is that how we solve our differential equations? Now we find one, we find another, we show they're linearly dependent. Is that what we do for our higher order differential equations? How do you solve your higher order differential equations? What did you do on the exam to solve them? Auxiliary equation, found your values of m or r. I mean, that already assures you that whatever you found was going to be linearly independent. It's going to be the same idea here. So the next thing I got is questions here, but I want to skip over that just to kind of breeze through the end. I'm just going to talk through this last part as a roadmap. We're going to do all of this in detail, so don't write this down. We're going to cover this in much more depth. But I want to show you the similarities here, okay? So don't write it down, but you don't got to pack up right away, right? Give me a minute here. 2 minutes. Second order differential equation. How do we solve this thing? We assumed that x was equal to e to the rt. And then we took the derivatives and we plugged it in to generate an equation that looked like this. That process was really important on that last problem on the exam, right? That assumption is the important piece, right? And then taking the derivatives, plugging it in to generate this magical auxiliary equation. Okay? Same thing over here. All we're going to do is assume that u looks like, boy, I don't know, how about some constant, but probably a constant vector now, e to the rt. That seems like a reasonable assumption. And we're going to take the derivative and we're going to plug this in. But when we plug it in, we're going to get a different kind of equation. We're going to get an equation that looks like this. It's going to look like a times c equals a times r. And if you look at that equation, you might have seen that equation before, where you take a matrix times a vector, and it actually gives you the same answer as a matrix. I'm sorry, it's all goofed up here. How about a times c equals c times r times c. When you take a matrix times a vector, it actually gives you the same result as a scalar times a vector. Do you know what equation that is? That is your eigenvalue equation, eigenvalue, eigenvector equation. So we're going to make this assumption. It's going to generate this equation. In the end, we're going to find out that R is going to be the eigenvalues of the matrix. We're going to find that this guy is going to be the eigenvectors of the matrix. That's how we're going to find our parameters. We assume this guy. We find the right parameters to form our solution. We assume this guy. We find the right parameters to find our solution. In this case over here, R had 3 different cases. R was distinct. It was repeated, it was complex. Over here, lambda is going to be distinct, repeated, complex. And they're going to have different solutions. Exactly the same thing for systems. The process is going to be just the same, but it's going to be more linear algebra, and those eigenvalues and eigenvector calculations are going to be important. Okay? So a good place to review if you want to get ahead of that is to review those calculations. Okay. I'm going to send out a homework sheet for Thursday. It's going to have just a couple of short problems.